In our final lecture, we're going to discuss an issue that we've been sidestepping throughout the course for the most part, but is an issue that pretty much touches on most of the models that we've been discussing, and that's the issue of model selection. So we've already seen with many of the models that we've been discussing that there are certain parameters that we need to set in advance. And we haven't discussed in too much detail how to go about setting those parameters, but we did briefly touch on the general approach of cross-validation. And so we saw how we could hold out parts of our data and then learn models on the other parts of our data for different parameter settings, and then see how well we do on the held out test set. So that's the general idea of cross-validation. Another model selection problem is determining the model order, and this is a little bit different from determining model parameters in that we have to actually decide the model to begin with. So for example, with the Gaussian mixture model, we have to decide how many Gaussians are we going to learn. With matrix factorization, we had to determine the rank of the matrix factorization that we were going to learn in advance. And for hidden Markov models, we had to define how many states we were going to learn in our model. So these problems are a little bit more than just simply learning how to set a particular parameter for the same model. It's learning how to choose the model to begin with. So this is the model selection problem. There are many ways that we can handle this issue. Cross-validation is actually still one of those ways. In this lecture, I'm going to focus on two new ways for handling the model selection problem. So in each of these problems of determining the model order, we can't simply look at the log likelihood of different models for different orders, because we can always fit our data better with a more complex model. So we need new techniques. So in this lecture, we're going to discuss two approaches to selecting the appropriate model order. This is different from selecting the appropriate model type as follows. So for example, here are two potential data sets that we could have. If we want to learn a Gaussian mixture model on these two data sets, in the first one, we've picked an appropriate model. We could model this with a Gaussian, but we've picked an inappropriate model order by learning several more Gaussians than are necessary. So the data requires 3 Gaussians, and we learned 6 Gaussians in this case. So we picked the wrong model order, but had an appropriate model type. In this plot on the right, if we wanted to cluster this data into 3 clusters using a Gaussian mixture model and the original data space, we could argue that we haven't even picked the correct model type to begin with. So a Gaussian mixture model on this type of a data is inappropriate to begin with, and so selecting the correct number of Gaussians or the correct model order is not even an issue that we should discuss. We should first find the correct model. So in this lecture, we're assuming that we've picked an appropriate model type. We're assuming that if we're working with a Gaussian mixture model, that is an appropriate model to be working with. And now we're interested in picking the correct model order for that model type. To do this, we're going to work with this type of a model setting. So let's set some notation. We're going to write for L the log likelihood of a parameter under a model. So we have this type of a model assumption. We're going to assume that we're getting data xi drawn iid from some probability distribution on x given a model parameter. And now we want to think of the log likelihood of this data. So this is something we've discussed very early in this course, which we can write in this way. So the log likelihood of a sequence of n observations that are iid from this probability distribution is just the sum over each of the log likelihoods on each data point. And now the maximum likelihood solution for this, as we discussed in the first lecture, is simply to find the value of theta that maximizes this log likelihood term. So if this is the setting that we're working with, and we are, for example, wanting to learn how many clusters we should learn in our Gaussian mixture model, so in that case, this likelihood would be the Gaussian mixture model likelihood, and theta would be all of the parameters for the different Gaussians as well as the mixing weights on those Gaussians. The incorrect way is to go about trying different Gaussian mixtures, different model orders, maximizing the log likelihood, and then picking the best one. So we can't simply try a Gaussian mixture with 3 Gaussians, 4 Gaussians, 5 Gaussians, in each case learn the log likelihood, learn the maximum of the log likelihood, and then pick the best performing one, because we're always going to be able to fit our data better and better with a more complex model. So for example, if you want to immediately see this, we can perfectly fit the data by simply picking n Gaussians in our Gaussian mixture model if we have n data points, and putting a Gaussian centered on each data point and then letting the covariance go to 0. In that case, we can perfectly fit all of our data. We can make our log likelihood go to positive infinity, but that is going to overfit our data. And so a more complex model overfits our data, and so we can't simply look at the log likelihood in order to pick the best model order. And so we need more technique, a better technique.